So, hi, how are you? Hi, RubyConf Uruguay. So, thanks for inviting me. I'm not going to dance. I'm not going to ask you to raise your hand. Let me tell you 3 short stories in 3 minutes, which I think has to do with the fact that we're all here. When I was preparing the presentation and before my talk, I realized that I have been attending conferences for 15 years already. And the first dates back to the first conference I attended. So this is back in 1999. For some years, I had been working with open source, with free code at the company where I was. And then a colleague and a friend, we decided that it was interesting to attend this conference. O'Reilly had announced that they were going to organize an open source convention, that they were going to integrate Perl, Python, Linux, Apache. It sounded great. So we traveled there, Monterrey. This is an old convention center. We were quite tired and had to start early next day. So we decided to go and have something to eat. And when we were there, this person came up. He sat with us. Where do you come from? We're from far away from Buenos Aires. Well, how interesting. And he was from Australia. He said, wow, Australia. There are a couple of tools from Australia that we use all the time. Our Sync, which is for synchronizing files, and Samba, which is a famous file server that are compatible with the Windows network. Well, this is from, I'm under Twitter. So it was that guy. So we hadn't even begun with the conference, and we were already spending time and sharing opportunities with people who were really working on things that we were using. The second story is a conference which I didn't attend, but it has to do with why I ended adopting Ruby. In August 2005, my friend Juan, who went on going to these conferences, and when he came back, he said, well, Perl and all that. And the interesting thing was this guy who spoke about a blog, and he does it in 15 minutes. So the blog was done in Ruby, and by him. In 2006, there's a full program on Ruby talks at the OSCON, and in 2007, we have the first RailsConf, which is the second one, in fact. And the interesting thing about that conference, which I could attend, were the people there. There was something, the people were thinking about the same kind of problems. So Ruby was being criticized, and the impression was that people who were there were going to solve our problems. And then this is a third story, which has to do with the fact that we are here today. And this is RubyConf Uruguay last year. We came with a group of 5 colleagues and friends. And this was the first time that I came to RubyConf in Uruguay. And in one of the events after the talks, I spoke to Jose and Santiago, whom I had met at previous events. And it was great, and I joined their team, and I moved to Uruguay. That is where I'm now. Now, the point is that you should make the best of the opportunity of being at this conference. This is a technical presentation, but you have to really realize that this is not about technology. It is the networking opportunities that you have before, during, and after the conference. So if you see the organizers and the sponsors and other participants, so please thank them, because this makes things happen. So I will now continue what Sebastian's presentation stopped. He said how unrelated systems can speak with one another. And this presentation stresses the fact of how to communicate and interact with processes and programs that are related. A bit of history, we continue traveling. July 1969. This was 43 years ago. Man set foot on the moon. This was the most amazing journey that humanity ever undertook. Now, how did they get there? There were two computers. This was the computer that guided the Apollo mission. This is only the keyboard and the screen. It weighs more than 30 kilos, and although they tested it very many times, at the most critical effect, they had to restart it. These computers had 2K RAM and 36 ROM. That was all they had. And rapid calculations shows that all the operations for more than 1 week, any laptop that you have can be done in 1 second today. Okay, 2K. That is all. That is what you see there on the screen. And the other interesting thing is that it could run 8 processes that were prioritized at the same time. And at the same time, in the laboratories of the Bell Company, a team was working on the OS that they wanted to have. At that time, the applications and the systems were much weaker. Each application began with a project of preparing an OS for that application. The team is wonderful. You have Ken Townsend and Richie, Rick Morris, Susanna, and many other names which are still active today. And this is with the excuse of preparing a system for an application. So the team receives this machine, and in 2 years they managed to finish the application and the OS. November 1971, 2 years later, this is what determined the first edition of the Unix OS, and many of the central ideas were already there. This is a page of the manual of the handbook dated November 3rd, 1771. This is a format we're used to, but the only difference is that the system was not on C. So these are queries to the system, calls to the system. But once again, the important ideas were there, and these are the same ideas that continue solving problems today. And this is now the topic of my presentation. How can we do Unix programming in Ruby? And how can we take advantage of Unix language that is available in Ruby? And although Ruby has a very clear origin in Unix, there is a strong tradition as to how we teach this and how we learn this. And it ignores this. The most important documentation of the language itself by Flanagan and Matsumoto is more than 400 pages long, but only 5 pages are dedicated to Unix. On the documentation and the examples of the libraries, so it is quite surprising that because one of the fundamentals of Unix is write programs that work well together. The power comes from the relationships between the programs and not from the programs themselves. So these are different quotes. So this tradition seems to ignore all these facts. A first question. Now, what does this code do? There's not much time, so this is like a minimum that you require to write in Ruby. It's a command. Now, what we will see in this presentation very rapidly, processes, signals, pipes, which is one of the latest adds to the basic core of Unix, and some examples of code and libraries. Let us start with the processes. This is a basic execution unit that you have in Unix, and the difference with a program, sometimes we use the words in one way or the other, is that this is an instance of a program that is being executed. We can have different programs, processes in a program. They're all created with a fork placed in Ruby. So process fork. Fork is a method which I call and comes back twice in my process and then in the new process.
If we run a conditional, We don't know whether it's true, it's a lie. It comes out through a branch of the conditional and another. What is happening is that in the system call, part of the process is recreated and the other part of the process goes on in the point where it had stopped. All the processes have an identifier, a number. In practice, that number, it's a relatively low, but in the new ones, you have larger numbers because the capability has increased. A process can ask for its own identifier, asking for the PPID, and it can also ask for the father's process that created it. So the two processes can know who each other is, who the others are. So this process, it's the first exit of the conditional, it's the father, and the father can learn about the son and the child can learn about the parent. So before using that, one of the things you have to be careful with is that the whole status of the process is shared. So a trivial example that calls fork 3 times doesn't create 3 processes but 8. To protect ourselves from that, there's another fork form that accepts a block and guarantees that, as well as in other parts of the standard libraries, there won't be anything outside that block. There we call fork 3 times. We have 4 exits, 1 of the parent and 3 of the child. So how does this impact the life cycle? What does a process do when it's created? There are 2 options there. The first thing is that the mission of all the processes is to finish, and when you finish, to have an exit code. 0 code has no errors, and a code that is not 0 indicates error or an abnormal exit. The mission of a project is to give the parent the exit code. If it survives, then the process can continue with its normal life. The father, waiting for the exit of a process, has to call the wait system and receives the code that it gives to the child process. Visually, if the child process finishes after the wait will call the parent process, waiting, as the call says, until that code is available. If it's the other way around, and the child process finishes before the wait call, the process will continue to be in the system until the code can be delivered. That status is what we call a zombie process. That is the status of a process where they haven't solved the code yet. One possibility is to see whether the code is turning around with the code. But anyway, it's not a good idea to get this full of this. If I want to ignore it, for instance, if I'm doing a common practice that's called to fire and forget, I may, this is a simple case, a zombie would stay there. And if I wanted to avoid that, this corresponds to the 2 previous images. I could wait for the process, and if not, I have this other choice, that is to detach. Detach is a method in the process model that will create a thread that will wait and wait for that code, so I can continue to do my things without worrying. A demonstration to use detach. I use the child process, and even if my process blocks it, the process will not stay there turning around and around. Another variant of the wait is the wait all. Not only is it going to give me back the code of the child process that has just exited, but it will also give me the exit call. If not, I would have to do a query. It is useful because I can do 2 things in the same call. And in this case, I fire 3 processes to mimic that I'm throwing 3 dice. I generate 3 numbers at random, and in all the exit codes of the child processes, I can see the status of each of exit. You can't speak of fork without speaking of copy and write. It's a characteristic of the Unix systems to save memory when doing forks. So if you're going to use a lot of fork, use Ruby 2.1. There are very significant changes in the garbage collector and the garbage bin that considerably reduce the consumption of the use of memory. There are many things that don't happen any longer if you use this new release. And the other advice is, as the files and all the status is shared with the children processes, the sockets or the pipes or open files will remain open in the child processor. It's not a bad thing. Sometimes it's good. For instance, if two processors wanted to alternatively write in a file, if one is using a connection to a database, he doesn't want the queries to be answered in the other processors because it can have a bad conclusion. So before and after a fork, connect and disconnect. A language that is very common to Unix is daemons. Those are long life and processes with no interaction. We have the daemon process that enables me to do a process without the previous. And in Ruby before Ruby 1.9, I can call just one single method and have the same results. The other Unix language, once I create a new process, here I'm speaking of copies of my own program, I can run another program in that process that I created. And I can now I created a new process and I'm going to change the program. The system call is exposed to the process method, the exec method. I call exec. And in the same process, without creating a new one, the program is replaced by another. In code, after calling exec, nothing else will run because the program will be replaced by the other image. And this takes us to another issue of a Unix program that we see now, and it's that of signals. Signals are software interruptions. Those are notifications of the program, either because users enter or hardware or memory violations, etc. There are a number of signals, historically, tenths of them, and the ones that we are going to care about are a limited number, less than 10. One is a signal that shows that the child process died, and the signals of interruption and exit that are caused by request of interruption of the process by the user, and the termination signal, the term signal, and the 1 and 2 user signals that helps us communicate between the processes very simply. These can be used in long life interfaces, for instance, to rotate a registry file and to reinitiate the child processes. Now, so the signals have two parts. One enables me to capture a signal or to reestablish it, and that is available in the trap method in the signal module, and the other called a system that is one of the worst possibilities you have with Unix, that is called kill. Actually, it should be called something like send signal, but historically it's known as kill, and it's available as kill under the module. In this case, we create a child process, and in that process, we are going to accept giving a behavior to the signal, to a trap signal. The process waits and waits, doing nothing, and we send a trap signal to the process. Something that is important that needs to be taken into account when we are processing signals in our code is that the code that we use to receive signals needs to be a re-entry. Without giving you the details, there is a possibility that the code that we are developing may receive signals at any time, even when processing a signal. And this in Spanish means that the code that we are going to write for a signal needs to be minimum. You have to do the least possible, and it should be able to be executed without undesired consequences. In a simple example, here I'm accepting the signal user 1 and increasing a counter.
This calls in the problems, and an alternative implementation that is more accepted is to save these signals in a queue, and these are then processed. There are less structures in the same place. Now, in this example and the previous one, if you pay attention, you see the result of running it. Although we sent 1,000 signals, there were 300 in this and 507 here. Because this is because these there are no queues of signals, but this is like a delay, an indication that there is a signal there. If a signal is being processed and there are 5 notifications of the same signal, then the process doesn't receive 5 calls. It will probably receive only one. So that leads us to the final Unix language, which was that of the pipes. This is quite a late incorporation to Unix. This was in 1973. And thanks to the insistence of McEnroe, Thompson, Adsis, and the following day, when they received to reach the office, they start to assign the commands, and that is where the toolbox idea came up, how to train the commands to do useful things. So the pipe communicates related systems, processes, and this is a command line and makes this work. So graphically, what is happening is that you have the ls command and the more command have a common parent who then supplies a created pipe. So it connects the out from one to the in of the other. So none of the processes realizes that what is happening there one directional, but in Linux these are usually accepted as unidirectionals. What is written on one side is read on the other, and they are atomic in writing. So if I write less than 512 bytes, that message would be interrupted and received in 2 different parts. Of the 3 user cases in Ruby, 2 are in the open system under the I/O method. This is the strangest one of all. I never really found much sense to that syntax. So this opens a pipe in the same process, but behind it is doing a fork and connecting the output of that process, the child, to the descriptor that is received in the pad side. Now, the second one is more practical and easier to read. You send a command that will be interpreted. A process is created, the command is executed, and then it is connected. Now, the most interesting form is what is called the I/O pipe. This will return 2 descriptors that are connected with each other. So I return a pipe. And how do I use this? I call and receive the 2 ends. I can write twice, read twice, and of course, this is blocked. And if I ask for more than what I wrote, it is one single process, so no one else is going to write there. I have the opportunity of adding a ready method to the descriptors to consult if there are data that has to be read. In this example, I create a pipe. I write 10 times and I read 10 times, or I write 10 times first and I read 10 times afterwards. Now, if this is similar to a file and is not supported in storage, well, the capacity is limited in terms of storage, temporary storages in the core, and it is limited. This is an example run in a Mac. After the 64K, the pipe starts to lose data. Now, although there is a specific use of the pipes for the same process, everything is far more interesting when one tries to use it with more than one process. And basically what happens that there's a shared stage after the fork, and then this also provides the shared pipe with a father and child process. So here you have the 2 ends of the A process, and these are also in the A prime. And the technique aims at closing the part I'm not interested in the parent or the child. And I keep the ones that I'm interested in. We create this 3 times. In the child, I'm not interested in reading this. I'm only going to write, and it sends messages that are collected by the parent on the other end. I can also use it for reading and writing. This is as follows. After the fork, this is what it looks like. We eliminate the ends I'm not interested in. And then I have a writing channel and one for reading. So I call the pipe twice. I close the end I'm not interested in the parent and in the child. So I have a communication. Here you have a message that leaves from the father to the child. The child generates this, and then this goes back to the parent. And this can be done with more than 2 processes. It is more difficult to show it in a schematic representation than writing it in code. But it is possible to have these networks of pipes to speak with processes I created. And the way to access this parallel reading of the descriptors, which I'm not sure if I can read or not read at the moment, is done through the select call. This is in the I/O module, and we saw this in the previous presentation. So the select allows me to do things such as these. I create 5 processes that will end in different orders, and I need to wait until these are finished. I can start receiving them with this code here, which will show me which are ready to be read until there are no more. So if we got this far, we can say that they were sufficiently dangerous to produce a lot of harm. We're going to run very rapidly through some of the standard library and some schemes which allow us to read codes which solve things. The first one is in the standard library and is not used very much. It is Open3. This allows you to coordinate access to the entry, exit, and connection to the processes errors, and it allows you to write code as simple as this. I can call an external command, send in entry, input data, detect the error, and the exit or output status. And it is quite simple. Another example was taken from QTest. And the part of the code that is run in QTest is for testing. This is a micro-testing library. And in the you have code as simple as the fork you have there and the load. The rest is capturing the exceptions, and the method that waits and collects the run of this test is called wait. It is the same thing that we saw in the previous examples. Foreman. That gives life to Heroku and allows you to do coordination of different processes. In the Foreman code, you have things such as a kill call that captures an exception and then an interesting case. And instead of sending an exception, sending a signal, to a given process, has a return code that allows me to see if a process is still going round and round. And this is what is being done through the rescue line. So the conclusions that we can draw from this presentation is performance, security, etc. were solved in this way. Libraries such as Unicorn, Rescue, Foreman continue using the Unix principles that are still valid and have been valid for the past 43 years. Use the correct tool for the proper job, and nothing of this will disappear tomorrow. Even if you weren't using Ruby, these are concepts and languages that are valid for your work every day. Thank you very much.